Hi there, my name is Spencer Buja. My team and I have been working on the Social Recipe Recommender for the CS411 class. It's a database-driven application for exploring and sharing recipes. Okay, so here's our recipe app. So first we're going to open up the app, and we're greeted with this sign-in page. If you haven't created an account yet, you need to click up the sign-up link and put all of your information in. I've already done that. So now you're going to type in your username followed by your password. Okay, we've done that, and now we're going to log in. After signing in, you'll see three main tabs, and these tabs are My Recipes. These are the recipes that the user has favorited. Next is the Explore tab. These are all the recipes in the database sorted by the recommender system. That's how they will be ordered. And then finally, we have a Messages tab. Just to show how we are able to read and select from the database, this My Recipes tab is driven by a favorites table, so this image and its associated ID is pulled from the table, and then when you double click on this image, you can pull up the actual recipe itself and some details about that, and finally a personalized note from the user. So as I mentioned, the next tab is the Explore tab, and this tab pulls all of the recipes from the recipes table. And what it's doing here is it's pulling the main image and the ID of the recipes and showing and displaying them on this page. Like the My Recipes tab, you can double click or tap on an image and open up the details about the recipe, which shows a link, the name of the recipe, a summary, and then a note if you favorited the recipe. And here we haven't actually favorited this one yet, so there's no note here. Okay, let's try favoriting a recipe. So we're going to click on this heart, and what this heart does is it inserts this recipe ID and a user ID into the favorites table. And now when we go to the My Recipes tab, you can indeed see that the pork and black bean stew has been favorited. Okay, so we've favorited this recipe, and that's why there's a colored in heart here. And so this recipe is in the favorites table. Now let's try deleting this recipe from the favorites table. So we will unheart it, unfavorite. Okay? Now we go back to the My Recipes tab. The pork and black bean stew is no longer there. I will say that on the Explore tab, the pork and black bean stew will still show up because we've deleted the record from the favorites table, but we actually haven't deleted the recipe itself, which should be expected by the user of this application. Okay, in this next section, I'm going to show you how we're updating records in the database. So here we have the New Brunswick lobster casserole, and we're going to favorite it. Now let's open up My Recipes, and we're going to see the New Brunswick casserole, lobster casserole in here. And we're also going to see an empty section for notes. So right now in the notes table, there's no record here, so let's first just do an insertion into this table for the key of user ID and recipe ID combined. This looks pretty good. Okay, so that's the first time, it's the insertion. Now let's go back. You can see it says this looks pretty good. And let's try to update this. So, okay, I love eating lobster. Okay, so now this updates the record in the database. And you can see that it says I love eating lobster here.
I'm now going to talk about our advanced functionality. We decided to build our advanced functionality to allow users to explore recipes or get recommendations of recipes using various machine learning techniques. Given the large number of recipes, we wanted a way to recommend user recipes based on the prediction of what they might like the most. We built a content-based recommender system for this. We used our SQL databases and various NLP techniques and machine learning packages in Python. When the user opens the Explorer page, we provide recommendations to users based on the similarity of the text data on their favorite recipes compared to the other recipes with images in the database. So for example, for me, I have previously favorited a number of different recipes around ingredients of steak or lobster, and as you can see, based on that, given our recommender system, we're getting a lot of recommendations for similar sort of recipes as well. Specifically, what we're doing is recipe ingredients, summary text, and titles are cleaned and lemmatized and transformed and fitted as word vectors. These vectorizations are based on each word's frequency in each recipe itself, as well as the inverse frequency of the word across every relevant recipe record. We then calculate the cosine similarity of each recipe against the vector of the user constructed using the recipes the user has already favorited. We can then further enhance this by weighting also what the user has previously rated and recipe word vectors around those recipes as well. Note that we wrote our own code to calculate the matrix multiplication and doing all of the techniques of cosine similarities and other NLP and cleaning of the data to avoid using many hefty Python packages that slow down the system. Finally, we recommend the recipes to the user based on the highest cosine similarity when the user has not favorited any recipes before. We recommend a random mix of recipes to avoid the cold start problem. Beyond just explore, which is suggested recipes using our machine learning technique, we also allow users to search for recipes across the tens of thousands of recipes that we have. So a user can come in and search for a recipe, and they are sorted based on their average ratings whether the recipe has an image or not. As you can see, I searched for green beans. I'm finding the top recipes that have a particular rating.
We wanted users to be able to send messages and share recipes to one another within the application, so we created a messaging system. The key technologies used for storage in this messaging system were a NoSQL database, MongoDB, and the SQL database, MariaDB. Additionally, a key technology that we used for sending messages quickly between users over the network was Socket.io. So for the structure of the messaging system, we use a single entity in the NoSQL database, which is the message. And the reason why we chose the NoSQL database for message is the requirements actually change throughout the implementation of the messaging system. So it was actually really nice to be able to modify what we wanted to store in the records as we were implementing the system. And then what we needed to do is we needed to combine the results of the SQL database, which has the user entity, and combine the IDs at the application level. So that was the key challenge of combining the IDs between the NoSQL database and the SQL database. If I haven't sent a message yet before to another user, this other user won't show up on the screen on the Messages tab. There's no historical message, so I have to somehow look up this other person. To solve this problem, we enabled string-based search over usernames. I type in another user's name in the iOS client, for example, Claire, and we search against the MySQL database for this username using a regular expression. This enables us to return relevant results even with a partial name. So here we have Claire and Claire Mullins as the usernames. When the Messages tab opens, the client looks up the single most recent message between the user and their friends. The server uses the user ID that the client provides and finds the most recent message in MongoDB, using a datetime attribute in the document between that user ID and all other user IDs sent or received by that particular user ID. So, for example, the last messages that I sent to Atif and Dikra were both sharing a recipe. So we can click on Dikra here, and as you can see, I sent him a recipe for prawn biryani. If I typed in a message, then on the screen it would say that the last message I sent was hi. If I click on Dikra and the screen opens, it shows all messages that have been sent or received between Dikra and I. When I message another user, the other user receives the message in near real time. We leverage Socket.io for real-time messaging. Socket.io uses WebSockets for pushing messages from the server to the client and vice versa. If it cannot use WebSocket, then it falls back to HTTP long polling rather than doing the server-based push. After the messages are sent, we log our messages in MongoDB so the client can load any message the user has received. So for a quick demo of this, I'm logged in as Spencer Bouja with username SV, and I want to message Claire. So I open up Claire and I type in, let's collab together. Cool. And then I send it over, and then it instantly shows up on Claire's screen. And Claire responds back with, that's cool. Let's do it. As a social application, the user can browse through recipes and share a recipe page to any other user. The share recipe data is wrapped into a JSON object and passed through the same channel as the real-time messaging Socket.io infrastructure. The client will parse the message differently as a shared recipe message bubble for messages that have a share recipe content.
We decided to use the following advanced techniques in our project. We used table partitioning, indexing, unique constraints, index on text tables, views, triggers, and stored procedures. We decided to partition our user table. As part of that, table partitioning on MySQL was a bit of a learning experience, since for doing that we have to drop all foreign constraints, key constraints for that table. And additionally, the partition field, which for us was the birth date, has to be part of the primary key and also the unique key that we defined for that table. We decided to partition the user table on the month of the birth date and maintain 12 partitions in the hope that the volume of the data in each partition would be relatively equivalent. We also decided to create text indexes on our recipe table. This allows for greater searching and also text indexing on our recipe table. The next technique we used is to create a view across our user favorites. This is used within our application to get all of the favorites that a user has for its favorite recipes. The next two techniques, which are somewhat tied together, we use are triggers and stored procedures. For triggers, we decided to use two types of triggers. One, we created a trigger on create date on the user table so that when the user is inserted, the created date is set. The other two triggers that we created are on the recipe rating table so that when the recipe rating is inserted and updated, we call a stored procedure that we created, which will update the average recipe table. For the we needed to create these two stored procedures because MySQL does not allow for a update insert stored procedure. So we specifically, I should clarify, it's MariaDB that doesn't allow for that. And then we created a singular stored procedure which updates the average rating for a specific recipe. We created this stored procedure so that we could maintain the logic of the average rating in a single place, so that if we ever wanted to go to a weighted average rating or something else, we could do that change in a singular place. The two stored procedures get updated, the two triggers get called when a user inserts or updates a particular recipe rating, and that calls our average rating to be updated. Right now, the average rating table is used purely for analytical purposes. We imported data from two different data sets. The initial import was done by doing a web scraper against allrecipes.com. But that resulted us in not having enough volume of data. This was mainly because as we ran the web scraper, some web pages would error out with no data from the website. We troubleshooted this to be a problem on that website. We wrote the web scraper to bring in all the metadata for recipes that are part of the schema.org that are defined in the web page. To augment the data that we were getting from allrecipes.com, we decided to import in a data set from Kaggle. That data set had recipe data and also had user ratings. But the challenge was that we now had to seed our database with users for the user IDs that we were getting ratings for. We did that through a script. Importing both sets of data gave us a total recipe count of 250,000, which is well within. I'm going to talk a little bit about changes to our schema after our earlier submission. We added unique key constraints for username and email address. Previously, the user table just had primary key of user ID, but since there were no other constraints, a user could be inserted with the same email address or username. We also created a average rating recipe table. We decided to create this purely for analytical purposes, but later on it could be repurposed in our ML. We also decided to add on our user table created on date, which we would update through a trigger. Our average rating recipe table